In this video, we're going to take a look at section 4.2 on logarithms. Here's the definition of a logarithm. Log base a of x equals the number of powers of a, the base, that it takes to equal x, whatever is inside of the logarithm. So let's take a look at some examples to see how this definition gets applied. So here we're being asked to find log base 4 of 256. So what we need to ask ourselves is, how many powers of the base, which is 4, how many powers of that does it take to get 256? And so if you think about numbers being, not numbers, let me say it the other way. If you think about 4s getting raised to different powers, that's the way we want to look at it. 4 to the first power is equal to 4. That's not 256. 4 to the second power is 16. That's not 256. 4 to the third power is 64. That's not what we're looking for. But using a calculator, you should be able to confirm this. 4 to the fourth power is 256. That's the result we were looking for because that's what's inside the logarithm here. And so it takes 4 powers of 4 to equal 256. So that is what the logarithm is equal to. Whatever that power is, that's the answer we're looking for. All right, let's try this one. This one's kind of backwards, so be careful with this. How many powers of 27 does it take to equal 3? Right, so this is log base 27 of 3. I should have said that first. How many powers of 27 does it take to equal 3? So we're looking at it this way. Our base is 27. How many powers of that base does it take to get an answer of 3? And so if you're thinking, how is this even possible? Because if we do the same exercise that we did over here, 27 to the first power is going to already be 27. We're already past the result that we're trying to get. If you go backwards, you could go 27 to the 0 power, which is equal to 1, which, by the way, will be relevant over here. But that goes too far in the other direction. So 3 is somewhere in between. So what you have to think here is, what could I do to the 27 to make it become a 3? Now you might say divide by 9, but that dividing by 9 cannot be expressed as an exponent. What can be expressed as an exponent are radicals. So something that you should know is, for example, a square root is the same as a 1/2 power. A cube root is the same as a 1/3 power. Right? So the square root of x, we can write that as x to the 1/2 power. Cube root of x, we can write that as x to the 1/3 power. So is there any kind of radical that I could apply to the 27 to make the answer come out equal to 3? The answer is yes, there is. Cube root. Right? The cube root of 27 is equal to 3. The cube root as a radical is going to be a 1/3 power. And so the answer here, how many powers of 27 does it take to equal 3? The answer is 1/3. And so that would be the result there. Here we're being asked to find log of 1. Now notice a piece of information is missing in this particular example. The base is not written here. Here the base is 4. Here the base is 27. Here there's no base indicated. So what do you suppose the base should be if it's not actually written there? A lot of students will guess 1. But remember, like we learned for exponential functions, the base actually is not allowed to equal 1. That holds true for logarithms as well. You might guess 0, but that's also not a viable base. And so it turns out that if the base is not indicated, the default base that we should assume is base 10. So you might not have guessed that initially, but this makes a lot of sense because our numbering system is also in base 10. So there's a lot of useful applications of having logarithms with a base of 10. And so if the base isn't written, if it's log and the base is not written there, the base is 10. So rewrite the problem, writing in the base of 10, and then ask yourself the same question. How many powers of the base, which is 10, does it take to equal what's inside the logarithm, which is 1? So how many powers of 10 does it take to equal 1? Well, 10 to the first power is 10. 10 to the second power is 100, so that's obviously not going to get us back to 1. If we go back the other direction, 10 to the 0 power, that actually is what we're looking for. In fact, any number to the 0 power is equal to 1, with one exception. 0 to the 0 power is undefined. But any other number to the 0 power is equal to 1. Which means, how many powers of 10 does it take to equal 1? The answer is 0. And so that's the answer that we're going to use here. What I was about to say, however, is what this tells me is that log base any number of 1 will always equal 0. Doesn't matter what the base is. Oh, I kind of messed that up. Let's try that again. Doesn't matter what the base is. Log base anything of 1 equals 0 every time, which you can apply over here. So this is a different kind of logarithm. It's still a log. I mean, I should say it's not a different kind of logarithm. It's still a logarithm just like all these other ones, but it's a different way of indicating a logarithm because it also has a special base. So ln stands for natural log. And whenever you see ln, again, the base isn't written here, but for natural log, it's not that we assume. Natural log, by definition, is log base e, which is Euler's number, which we saw in section 4.1 in the previous video. But it doesn't matter what the base is because log base anything of 1 is always equal to 0. So the answer there will be 0 as well. All right. So hopefully you feel a little more comfortable about what logarithms actually do. They tell you how many powers of a certain base that it takes to equal a given number. Right? So it's all about finding what the exponent should be to get a certain result based on whatever base is given. All right. The next topic, we had this in the last section as well in 4.1, is on graphing. Again, not my favorite topic to do in chapter 4, but it's part of the material, so let's go ahead and get this over with. It's probably going to take a little bit of time, though, to get through to talk about all the different aspects of these graphs. Here is what the graph of a logarithmic function will look like, a basic logarithmic function. So regardless of the base, they're going to have this same basic characteristic. They will go really flat as they go to the right when the base is bigger than 1. So the top examples here, the bases are bigger than 1. There's 2 graphs here. The yellow graph is the graph of y equals natural log of x. So the base there is e. We just talked about that on the last slide. E is bigger than 1. The red graph is the graph of y equals log of x. So remember, if it's log and the base isn't written there, that's log base 10. And so they're showing you how the graphs might look different from each other, but the basic characteristics are still the same. They both pass through the point 1, 0, right? Because if you plug 1 in for x, log base anything of 1 is always equal to 0. So that point will be there for every logarithmic graph, regardless of what the base is, if it's a basic logarithmic graph. Now, if you start adding other things here like +5, -3, things like that, the graph is going to move around. But for your basic logarithmic function, you will always have this point at 1, 0. The other thing that's happening is as you go to the left, you see there's a sharp curve here, and the graph starts to approach the y-axis without crossing or touching. So you will have an asymptote here, in this case on the y-axis, which is where x is equal to 0. So if you go back and look at the video for section 4.1, exponential functions, there was an asymptote on the x-axis where y was equal to 0. In, excuse me, in 4.2 for logarithms, it gets flipped around and the asymptote is at x equals 0 on the y-axis. Also, this point got flipped around because in 4.1 for exponential functions, we had the point 0, 1. For logarithms, we have the point 1, 0. So what this is actually telling you is that exponential functions and logarithmic functions are inverses of each other, right? They're the opposites of each other. If you switch x and y for one, you get the other. All right, so this is what your basic graph will look like. You have an asymptote here, passes through 1, 0. And then what we're going to be doing to graph the functions that we're going to have in this homework assignment is using transformations. So if you do have a +5 or a -3, you're going to take this basic graph and shift it or flip it over or whatever else is required based on what we see in the equation. If the base is smaller than 1, then you get all the same features. The asymptote is still here at the y-axis, which is at x equals 0. You still have this point here at 1, 0, except it's decreasing now. Right? So when the base is bigger than 1, it's an increasing function. When the base is less than 1, it's a decreasing function. All right, so you'll start, if the base is smaller than 1, you start with this basic function and transformations. If the base is bigger than 1, you start with this basic function and do your transformations. And while, again, the specific way the graph curves will be different depending on what the actual base is, it's still the same basic graph, whatever the base is when the base is bigger than 1. So for just sketching out a rough draft of what the graph looks like for using transformations, you don't have to worry about the base too much, just whether it's bigger than 1 or smaller than 1. Then when we go to like finalize the graph, then the base becomes important, and we will want to make sure to plot some points to get the graph exactly right. All right, so let's take a look at an example. So here we have this one's actually just a basic logarithmic function. We have f of x equals log base 6 of x, and they want us to graph this by first identifying some points on the graph. So they give us some numbers to plug in for x. We'll get the corresponding values for y, and then we'll go over here to plot the points. Again, when you're doing this by hand, you'll have to be aware of where the asymptote's located, and you'll want to plot these points and just have a basic idea of what the graph is supposed to look like. On Math Excel, it kind of does a lot of that for you. Again, the graphing tool is a little bit unusual. It's not like the graphing that we've done earlier in the semester. And I still have not made a video yet on how to use that graphing tool. I will try to do that after this video to let you know how it works, because it's really not that bad. It's just different. So I need to show you how it works. But let's say you're on the test and you're having to graph this by hand. How are we going to get that graph done? We're going to plot these points. So let's save the fraction for last. Let's start with this one, 6. I'm going to take x equals 6, plug it into this function. So we get f of 6 equals log base 6 of 6. So remember, we just did this exercise a couple slides ago. To evaluate this, to know what this is equal to, we have to ask ourselves, how many powers of the base does it take to equal what's in the logarithm? So how many powers of 6 does it take to equal 6? Sorry, supposed to be an equal sign there. The answer here is 1. 6 to the first power is what equals 6. And so we get 1 for this. Right, and that'll be our y-coordinate. So that gives us the point 6, 1 to graph, which will be right here. Right. And this actually is another rule that you can remember. Log base a of a always equals 1. So how many powers of a does it take to equal a? The answer is 1. So this will be true. If the thing inside the logarithm matches the base of your logarithm, the answer is just going to be 1 in that case. All right, let's do x equals 1. We'll plug that in for x. So we're going to get f of 1 equals log base 6 of 1. We just talked about this a couple slides ago as well, that no matter what the base is, log base anything of 1 is always equal to 0. And so we're going to get 0 here, which gives us that point that's on every basic logarithmic functions graph, 1, 0. Right? That point will always be there if it's just a basic logarithmic function. And then they have this fraction they want us to try out. So we'll have f of 1/6 equals log base 6 of 1/6. So what they're asking for here is how many powers of 6 does it take to equal 1/6? How many powers of the base, 6, does it take to equal 1/6? Right. Well, the 6's are already matching up, but what I would like is for the 6 to be on the bottom instead of on the top. So to get the 6 to flip over, we have to make the exponent negative. So we talked about that also in the previous video for section 4.1. So the answer here is -1, right? 6 to the first power is what gives me 6, but to get it to flip over to the denominator, I'll have to make the exponent negative. And so this is equal to -1. All right, so we get -1 here. And so we'll have 1/6 for x, which is going to be really close to 0, but it's positive, so slightly to the right, comma -1. So it's going to be like somewhere right here, right? And like I said, it helps to be aware that there's an asymptote located on the y-axis right here. And so we will draw a graph connecting these points. So there's going to be a sharp curve right here, and it's really going to stay pretty flat going to the right. But then going to the left, it's going to hit this asymptote, which means it has to keep getting closer and closer without crossing or touching. So it's going to look like this. So that's what the graph looks like. The domain, how far to the left does the graph go? Well, it gets stopped by the asymptote, so it won't go past 0, and also will not equal 0 either, so we have to use parentheses on the 0 instead of a bracket. How far to the right? Infinity. It goes forever to the right. So there's the domain. The range, how far down does it go? That's pretty clear. It's going to go down forever, so -infinity. How far up does it go? Well, that maybe isn't as clear. It's pretty flat at this point, but it continues to do this forever, mostly to the right and a little bit up. So it's going to keep climbing up just very, very slowly. But since it does that forever, it's going to eventually go to infinity. It just takes a really long time to do that. All right, and so that would be the domain and range. Let's take a look at one more graph, and then we can, we'll see, maybe 2 more. Okay, 2 more graphs. Actually, I think I'm just going to skip this one. It seems a little bit redundant. Now, the base here, or maybe I'll just kind of tell you the answer without going through all the details. You'll do the same thing we did on the last problem. What you should end up getting here is 1, 0, and -1. This is really just kind of the flipped version of the one we just did. Not inverse flipped, but the base is flipped over. So that's going to change the sign of our exponents, basically. And so what you're going to end up getting is for 1/6, you'll have 1. For here, we'll have 1, 0, and then we'll have 6, -1. And so it's going to have that same sharp curve. We'll still have the asymptote here on the y-axis, but going to the right, it's decreasing, right? Okay, I kind of messed that one up. Going to the right, it's decreasing, and it should be a little more smoothed out. And then going to the left, it's just going to approach the asymptote without crossing. So it's going to look like that. Okay. For this one, we got some more stuff going on. They give us some points to graph, so let's go ahead and do that. We'll start with 7 this time. So I'm going to take 7, plug that into the function. So I have -1/4 times log base. Did you guys remember? Do you remember? When I teach in class, I'll say you guys, like talking to the class, but for the video, that's kind of silly for me to say. But do you remember what I said the base would be? If it's not written there, it's base 10, right? And you don't have to actually write it, but you need to know what it is, right? So it's base 10, and we're going to plug 7 in for x. So we'll get 7 minus 6, which is going to give me 1. So I'm going to get -1/4 log base 10 of 1. But remember, log base anything of 1 is just going to be 0. So -1/4 times 0, still going to be 0. And so we just get 0 for this one. So 7, 0. Now what's happening here, if you think about it, is the graph is, if you think of your basic logarithmic graph, just log of x, the base is bigger than 1, so it's increasing. It's going to look like this. And it's going to have this point here at 1, 0. That's the basic logarithm. This one's not basic, right? We have a -6 here, which is actually going to shift the graph to the right by 6. Since that's directly on the x variable, it's going to shift it to the right. So this point that was at 1, 0 gets shifted to the right by 6. So it's going to end up at 7. And that's why you see this point right here. All right. The other thing that's going to happen is the graph is going to get flipped over because of the negative sign. And the 1/4 is going to cause the graph to shrink. And the only way to account for that shrinking is by plotting points, which is what we're doing here. But you should notice that it's also going to get flipped over, so it's going to look like this instead. Right? And then it gets shifted to the right 6. So that point will still be at 7, but it's going to look like this now. Oh gosh, I messed up. Right. It's going to look like that. Something like that. All right. On Math Excel, it'll kind of piece that graph together for you. All you have to do is select that it's a logarithmic graph, and then you're going to say shift it. You have to know this. You have to say shift it to the right 6, flip it over, do the shrinking, input all that information into the panel that they provide, and it automatically sets the graph up for you. So you're not even really plotting points on MathXL for these. You're just inputting the transformations. All right, now if we plug in 8, we're going to get f of 8 equals -1/4, log base 10 of 8 minus 6, which is going to give me -1/4 log base 10 of 2. Now, if we try to apply the same logic that we did for the previous logarithms that we evaluated, we're going to ask ourselves, how many powers of 10, so I'm going to write it over here, how many powers of 10 does it take to equal 2? And we are not going to be able to find an answer for that. We could maybe estimate it by kind of, guessing and whittling it down until we get something that gets us close to 2. But there's no good, nice, easy answer that works here. 10 to the first power is 10. 10 to the second power is 100. 10 to the 0 power is 1. 2 just gets skipped over. And so it's going to be a decimal. And the reason they're putting this on here, and also maybe you might have noticed on MathXL, they're asking, round it to 2 decimal places as needed. The reason they are able to get away with that here is because for log base 10 and for natural log, most calculators have those functions available as a button on the calculator. If it's any other base, if it's log base 2, that base normally is not available on most calculators. Now, there are some calculators that will let you type in whatever base you want. If you have one of those calculators, that's great. But most people are going to have calculators that only do log base 10 and natural log. So in this case, we can plug this into our calculator. Everybody should be able to do that. I did not prepare for this, so let me pause for a second. I'm going to go pull up the calculator, and then we'll see if we can type it into the calculator I have on this computer. Okay, so here's the calculator I have on my Windows machine, and I'm in scientific mode. And you'll see on the left-hand side down here at the bottom, it actually has both of those logarithms. It has log, which without the base written there tells me that's log base 10. And we have ln, which is natural log, and that's it. So I cannot directly find log base 2 of a number on this calculator. It doesn't have log base 2. It only has log base 10. So let's go ahead and type this in. Let's see if it'll let me type it in the way I want to here. So we have negative. I don't know if it'll let me do negative signs on here. Okay. -1 divided by 4 times log. So I'll go ahead and... Okay. So it didn't do what I wanted it to do. So some calculators, especially, I don't know, the better ones will let you kind of type it in the way you see it on my screen right now. But this calculator, though, notice what it did here. It took the 1/4, the 0.25, and when I hit the log button, it put that inside the logarithm, which is not what I wanted it to do. So the way this calculator works is I have to type the thing that goes in the logarithm first, and then hit the log button after. So it's kind of backwards. You have to enter the right part in first and then the left part in second. So let me see if I can try that again. So let's say we have, okay, it cleared it out for me. So I still have the -1/4 right here times, I want to do this logarithm. And even though the log is the part that goes next on my paper, for this calculator, I'm actually going to have to type 2 first, right? Now notice it didn't put that in my calculation yet. Then I will hit log, and then it sets it up the right way, right? So this is -1/4 log base 10 of 2, and this is going to be the result, I think. I don't know, maybe I have to enter here. Okay, now I have to enter. So the part that you just saw, the calculation you just saw, was just the log base 2, not base 2. The part you just saw was the log base 10 of 2, and then I hit enter to actually do the entire calculation. So this is what we get for the entire calculation. And we only want to go 2 decimal places according to MathXL. So -0.08, right? So again, I use this decimal place to decide where to round this one. 5 means I'm going to round that up. So it'll be -0.08. All right. And so I'm going to get negative. Whoops, I put 2 equal signs for some reason. -0.08 is the answer I get there. And so for 8, we get negative 0.08, which is going to be very, very low. It's going to be, sorry, I went the wrong direction there. Should be negative though, right? So it should be very, very close to the axis, but just below it because it's negative. All right, you do the same thing for 9. I'm not going to write it out on the screen, but I will go ahead and bring it up on my calculator if I can. Right, there we go. Whoops, okay, sorry about that. Okay, so let's do the same thing. Negative 1/4. And then to do the log, first I have to hit times. So times. To do the logarithm, I will first have to type the number in. Now, if I'm plugging in 9, I'll get 9 minus 6, which is going to be 3. So I have to type 3 first, and then the log. Now, this calculation you see on the screen right now is just the log base 10 of 3 part. To do the entire calculation, I have to hit enter, and I'm going to get this. So negative 0.12 would be the answer here. Negative. Let's try that again. Negative 0.12. All right, which again is going to be just barely below the axis, right? It's not a little bit further than the other one, but this is a little too exaggerated. Honestly, it's going to be much closer than how I'm drawing it here. Now, in order to draw this graph correctly, you also need to be aware of where the asymptote is located. And so the asymptote is, for the basic function, starts off on the y-axis, but then when I shift it to the right 6, it's going to end up at 6, right? Because it starts off at x equals 0. When I shift that to the right 6, it'll now be at x equals 6, right? And then if you flip it over, the asymptote doesn't move, right? So if you flip the graph over this way, the asymptote's not going to go anywhere. So it'll stay right there. And so it's going to be at 6, which will be right here, which I'm not going to draw very well this time. Okay. All right, so there's where the asymptote's located. So going to the right, it's going to connect these points, and it's just going to be very, very flat going to the right like this. But it's decreasing, right? Because it got flipped over, so it's decreasing like this. Going to the left, it's going to hit the asymptote right away, and it's just going to go, this is where we're going to get our sharp curve at, and it's just going to approach the asymptote without crossing or touching. So it's going to look something like that. So that's how you would graph this by hand. Like I said, the graphing tool on Math Excel is going to make this work a little bit differently. For the domain and range, how far to the left does this graph go? Well, it won't go past 6. And it actually never reaches the number 6. It'll get to 6.0000001, but it never ever reaches the number 6. So we have to use parentheses on that. How far to the right does it go? Infinity. It's going to go forever to the right. And then the range, how far down? It looks really flat here, but it's going to keep going to the right and down forever. And so it'll be negative infinity. How far up does it go? Positive infinity, right? And so that'll be the domain and range. And just to make it easier for you, the range for logarithmic functions is always negative infinity to infinity. All right, so now that we got the graphing part over, let's move on to some other fun type of problems. More fun anyways than the graphing. All right, in this set of problems, we are being asked to convert from logarithmic forms of equations to exponential form. Right? So when you're given an equation that's a logarithmic equation, the same information can be rewritten exponentially. Instead of leaving it written logarithmically, we can write it as an exponent. Right? So remember what a logarithm is telling you, right? Log base 3 of a is telling me how many powers of 3 that it takes to equal a. So in other words, the left-hand side here is asking how many powers of 3 does it take to equal a? Right. This is what we've been doing all along every time we've evaluated a logarithm. But this time we have an answer, right? It's telling me that the answer to this is b. It takes b powers of 3 to equal a. So the answer here is actually b. And so this same information can be written this way. This is telling me it takes b powers of 3 to equal a. I can also say the same thing like this. It takes b powers of 3 to equal a. Excuse me. My voice is kind of cutting out. It takes b powers of 3 to equal a. So that's how you write this logarithmic equation as an exponential equation. A shortcut that you can use that I like to tell my students about, this was not something that I knew ahead of time, it was something a student introduced to me, is they call it the loop. So if you ever want to go from logarithmic form to exponential form, you can use the loop. And the way the loop works is you start with the base of your log. That's going to become the base of your exponent. You raise it to the power of whatever's on the other side of the equal sign, whatever happens to be over here, everything, whatever it is. Then you set it equal to what's inside the logarithm. So if you follow that loop around, it will put the equation together for you. You start with the base, make that the base of your exponent, raise it to this power, set it equal to this. Right. So let's try doing the same thing over here. We have log base 10 of 1000 equals b. So we'll do the loop. We'll start with the base of my logarithm, which is 10. Raise it to the power of whatever's on the other side of the equal sign, which is b, and then set that equal to whatever's inside the logarithm, which is 1000. Right. And then you can stop and think, do both of these things say the same thing? Do they have the same meaning? This logarithm is telling me it takes b powers of 10 to equal 1000. This exponent's telling me it takes b powers of 10 to equal 1000. So they're both saying the same thing. All right, here, natural log, remember, is log base e of 6, right? Equals x. So I'm sorry, well, I said a little more than I should have there. So natural log is log base e. And then the rest of the problem stays the same, right? So we have natural log of 6 equals x. That's the same thing as log base e of 6 equals x. So I haven't asked you guys to do this yet, but why don't you pause the video, try to work this problem out yourself first, and then resume the video to see if you came up with the right answer. All right. So what you should come up with is you start with the base of your logarithm, which is e. You raise it to the power of whatever's on the other side of the equal sign, which is x. And then you set that equal to whatever's inside the logarithm, which is 6. And so this is what you should come up with for this problem. Right? So here we're going from logarithmic form to exponential form. Well, guess what else you're going to have to do? The reverse direction, right? So you're also going to be asked to go from exponential form back to logarithmic form. This one, there isn't a loop diagram that you could follow to kind of put the equation together for you. You just have to pick apart the exponential equation and fit it back into logarithmic form. So if I want to write this in logarithmic form, what I like to do is I first start by writing the word log. Then the base of your exponent becomes the base of your logarithm. So the way we like to say this, myself and some other math teachers I've talked to, we kind of joke about it because it sounds a little bit silly. But what we like to say is the base is the base, right? The base of your exponent becomes the base of your logarithm. So the base becomes the base. And then I actually like to skip over this part, and I do this part last. I skip over this part that goes inside the logarithm, and then I talk about what should go on the other side of the equal sign first. Because what I like to remember next, after the base becomes the base, is logarithms equal exponents. That's what logarithms are. Logarithms are essentially exponents. And in fact, the next section we're going to cover, 4.3, we really explore that concept. Right? So we'll talk about how logarithms behave. And they have this kind of weird behavior, but it's because they are exponents. So they behave like exponents behave. Right? So the logarithm here should equal the exponent. The exponent here is 3, and so the logarithm here should equal 3. And by elimination, the last thing I have left goes inside the logarithm. Right? So the 125 is going to go inside the logarithm. And that's how you put this together as a logarithmic equation. And again, they both have the same meaning. It takes 3 powers of 5 to equal 125. The logarithm here is telling me it takes 3 powers of 5 to equal 125. All right, we'll do the same thing with this one. Right? I'll start by writing out the word log. The base is the base. I skip over this part. The logarithm should equal the exponent. My exponent's -4. So by elimination, m will go inside the logarithm. And so that's how you convert that to logarithmic form. Now, if you leave your answer like this, if that's what you type in the Math Excel, it's going to count it incorrect, because something that you'll need to know is that log base e is the same thing as the natural log. And so it will want you to write it in that form. And so I'm going to rewrite log base e as natural log, ln. All right, and so this is what I would type into Math Excel. All right, so let's do the same thing here. Pause the video and give this last problem a try. Convert this exponential equation into logarithmic form. Once you've given that a try, resume the video and see if you came up with the right answer. All right, so what you should come up with here is log base 10 of x equals m. All right, so that's what your answer should look like initially. Now, if you stop there, you did a good job, but if that's what you type into Math Excel, again, it won't count that correctly, because it won't count that as correct, I should say, because log base 10 is most commonly written as just log, right? If the base is 10, the base doesn't need to actually be explicitly stated, and so they expect you to follow that same convention, right? So if the base is 10, don't actually write the base. Right? And so this is how you would type it into Math Excel. All right. Okay, just a couple more question types here. We have solving logarithmic equations or exponential equations using logarithms. And then we have finding the inverse of a logarithmic or exponential function. So just two more types of problems, and then we'll be done with section 4.2. All right, so the rule of thumb that I like to tell my students here is if x is in a logarithm and you're trying to solve for x and it's stuck inside a logarithm, convert the equation to exponential form. Right. So if you're solving a logarithmic equation where x is stuck inside the logarithm, converting it to exponential form will get it out of the logarithm where you can solve for it. Conversely, if x is stuck in an exponent, then convert that equation to logarithmic form to solve for x. So if you're solving an exponential equation where x is stuck inside the logarithm, sorry, not the logarithm, saying the wrong thing. If you're solving an exponential equation where x is stuck in the exponent, you convert that equation to logarithmic form, and then x will no longer be stuck inside the exponent. It'll be out in the open where you can solve for it. All right, so just remember this rule of thumb. If it's a logarithm, convert it to an exponent. If it's an exponent, convert it to a logarithm, and that'll help you solve the equation. So let's take a look at some examples here. So we have log base 5 of x equals -4. The most common mistake that students will make in trying to solve this equation for x is they will say, well, I want to get x by itself, so I will divide by this logarithm to get rid of it. So don't write this down. I'm going to erase everything I'm writing here because this is completely incorrect. But I want to talk about how not to do this problem because it's very tempting to think this should work. And so I'll see students on the test who didn't watch my video, who didn't come to class and listen to my lecture. This is the way they might think to do the problem. And then they do the same thing to the right-hand side. And then they get this garbled mess that really is just nonsense. Like this mathematically has, like I really struggle to find the proper words to describe how absurd that looks mathematically. And so this is the answer that sometimes students will give me, right? So I want to go back to, when do we use division to solve equations? We use division to solve equations to cancel out a multiplication. That's the only time we divide on both sides of an equation, is to reverse or cancel out a multiplication. This is not multiplication. Log base 5 of x is not the same as log base 5 times x. I know it looks like it's multiplying together, but this is not multiplication. It's no different than this kind of mathematical notation. This is not square root times x, it's the square root of x, right? It's an operation that you're applying to a number that's not multiplication. It's a different operation, right? So if this is not multiplication, division doesn't work to cancel it out. Solving this logarithmic equation like this, just to show you how absurd that is, like if, let's say I was trying to solve this equation here, like square root of x equals 5, right? It'd be like trying to solve this equation by saying, well, I'll get rid of the square root symbol by dividing the square root symbol on both sides, and then having this as your answer, right? This is absurd, right? So I think anybody that looks at this realizes like that just doesn't make sense. That has no mathematical meaning behind it. There's just no, it's just nonsense, right? Having an empty square root symbol that you're dividing by doesn't mean anything, right? Mathematically. That's what this looks like. It's complete nonsense. It has no meaning. So what I like to say is just like an empty square root symbol by itself is meaningless, an empty logarithm is meaningless. You can't have a logarithm without having a number inside it, right? So going back to this equation, the proper way to solve that is to use this rule of thumb. If x is stuck inside of a logarithm, like it is here, then convert the equation to exponential form. By doing that, you will get rid of the logarithm. You'll cancel out the logarithm and get x out in the open where you can solve for it, right? So that's how we'll cancel out the logarithm. We'll convert it to an exponent. And we're going to do that the same way we did a couple slides ago, just on those previous examples. You're going to do the loop, right? Start with the base of the log, which is 5. Raise it to the power of whatever's on the other side of the equal sign, which is 4, and then set it equal to whatever's inside the logarithm. And now the logarithm has disappeared. X is no longer stuck in the logarithm. It's out in the open. And now not only could I solve for x, it's already solved for x, but if there was more stuff going on here, I could then do more work to get x by itself, but it wouldn't be stuck in the logarithm anymore. Right, now, the one thing I do need to do here is simplify this. So 5 to the 4th power, it's kind of a big number. It's 625. All right, so x is equal to 625. So that's how you solve the equation. So don't do it this way. This is the way you want to do it. And again, it's not that hard to do, really. You just have to know the right thing to do here. So you convert the logarithm to an exponent by doing the loop. All right. So same idea here. We have 3 to the x plus 2 power equals 5. Now we actually saw exponential equations in section 4.1. And we had a technique that we learned in section 4.1 for solving exponential equations, which is to get both sides to have the same base. Unfortunately, that isn't going to work here. 5, I can't rewrite 5 as 3 to some power. If I could, that's the way I would go with this problem. So the first technique you should try to use on these exponential equations is to get both sides to have the same base. If that doesn't work, then you're going to use this technique. So remember, I was numbering the techniques. In 4.1, we had technique, I'm having trouble talking today, technique number 1, which is get both sides to have the same base. If that technique doesn't work, then you do this. You do this here, so this is going to be technique number 2. So this is where I mess up on the numbering of these techniques. So I didn't actually write it in my PowerPoint, but this would be the second technique. If you have an exponential equation and you can't get both sides to have the same base, then rewrite the exponential equation in logarithmic form, and that will get x out in the open where you can solve for x. All right, so let's go ahead and do that here. So I'm going to rewrite this in logarithmic form. So remember the process for doing that. So this isn't going to work. So I'm going to start by writing log. That's what we did on the previous examples. The base becomes the base, right? So the base is the base. I skip over this part for the moment. The logarithm should equal the exponent. In this case, the exponent is x plus 2. So that's what the logarithm will equal, which means 5 by elimination is what has to go inside the logarithm. All right, so that's how you rewrite this exponential equation in logarithmic form. And then from here, it's pretty easy to solve for x. It's just like a regular old equation now. So to get x by itself, you subtract 2 from both sides. Just make sure when you subtract the 2 over here to the left-hand side, you do not put it inside the logarithm. It will have to stay outside the logarithm. So my final answer here will be log base 3 of 5 minus 2 equals x. All right. Sorry, my voice keeps cutting out. All right. So this would be the solution to this equation. Okay, so how about we do another pause here? So why don't you guys try to solve this equation you, the viewer, by pausing the video, try to use the same technique we just used. It's an exponential equation, so try to solve this equation by converting it to logarithmic form. The only difference here is that in this case, they actually want a decimal answer, which means that once you solve it, you should be able to plug it into your calculator to get a decimal answer. So go ahead and give that a try. Even if you don't get the decimal part of it, just try to solve it for x and then leave it the way it is. And then we'll talk about how to plug it into our calculator in just a minute. So go ahead and pause it and give this problem a try. All right, so what you should be doing here is rewriting this equation as a logarithm. All right, this is an exponential equation. I'll convert it to logarithmic form. I'll start by writing log. The base is the base. Skip over this part. The logarithm will equal the exponent, which is 3x. That means 7 is what goes inside the logarithm. You guys had to do this earlier as well for one of the problems we did earlier. Not log. Actually, I think I did this one. You guys did log base 10. But remember, log base e is just the same thing as natural log. So you'll want to replace log base e with ln every time it comes up. All right. Of 7 equals 3x. All right. Now I can solve this for x in the usual way. It's being multiplied by the 3. So to cancel that out, I'll divide by 3 on both sides. And if this is where you stopped, this is still good progress. You did exactly what you were supposed to do, but this is what you should be getting initially. This would be our exact answer. So if they wanted the exact solution in logarithmic form, you'd leave it like this. However, in this case, they want the decimal solution. They want the approximate solution. That's what this symbol means. So I'll need to use my calculator to calculate that. So let's go ahead and give that a try. So clear this last calculation out. So I'll have to start, remember this calculator's backwards. I have to put 7 first and then natural log. And that tells me the natural log of 7. And then I want to divide that by 3. And so I get this result. So that's what you should come up with. They want us to go 4 decimal places. So 1, 2, 3, 4. The 5th decimal place is a 3, which means I will round this down, which means I'll just keep this as a 6. And so I'll have 0.6486. Let me see if I can remember that. All right, so 0.6486. I hope I remember that right. All right, and that's the approximate solution to 4 decimal places. All right, so one more problem type, and then we're done. Finding the inverses of exponential and logarithmic functions. To do this, we will use the same method that we learned for inverses back in chapter 2. We will use the switch and solve method. So remember how that method works. Step 1, you replace f of x with y, right? You just want to go back to using y as your variable instead of the function notation. And then step 2, you switch x and y, right? So everywhere there's an x, you put a y. Everywhere there's a y, you put an x. Step 3, you now solve for y. And by doing that, you will get the inverse. So after you solve it for y, that will be your inverse function. And then step 4 is you go back to using the function notation. So you'll use f inverse of x in place of y, right? And then that turns it back into, well, it's already a function, but that's using function notation to label that result. All right, so that's the switch and solve method. We learned it back in chapter 2. We're going to use it again here. So let's go ahead and give this problem a try. And so step 1, replace f of x with y. So I get y equals log base 10 of x minus 1. So remember, that's a 10. When you're typing it into Math Excel, you don't want to write the base 10 there. But when you're working with the logarithm like this, I think it's helpful to actually write the 10 there so that you have something to work with. All right. Then switch x and y. So everywhere there's a y, it becomes an x. And everywhere there's an x, it becomes a y. All right. So that's step 2. Step 3, we will now solve this for y. So we're back in the same boat we were on the previous few examples. We're trying to solve for a variable that is now stuck inside of a logarithm. So remember the rule of thumb for that, way back here. If x is stuck in a logarithm, convert the equation to exponential form. That's the rule of thumb that we want to use here as well, right? So y, of course, it's not x, but y, the variable we're trying to solve for, is stuck inside of a logarithm, so convert it to exponential form. And so we'll do the loop. We'll start with the base of the log, which is 10. That'll be the base of my exponent. Now here, the logarithm's on the right-hand side of the equation. This is the first time that we've seen that, but the loop still works, but it's going to look a little bit different. You raise it to the power of whatever's on the other side of the equal sign. The equal sign's over here this time, so we go to the left. We're going to raise it to the power of x. And then set that equal to whatever's inside the logarithm. So we're going to set that equal to y minus 1. So that converts the logarithmic equation into exponential form. And now we can more easily solve for y, because now it's out in the open. To cancel out this minus 1, we just add 1 to both sides. And I'll just continue my work up here. So we'll get 10 to the x power plus 1 equals y. And that's my inverse. Step 4 is to replace the y variable with the inverse notation. And then the other side of the equation stays the same. And so that is my inverse function. All right. So why don't you guys give this problem a try? Pause the video, work out this problem, find the inverse, and then resume the video to see if you came up with the right answer. Right. So the first step here, replace f of x with y. So we get y equals 2 to the x plus 9 power. The second step, you switch x and y. So everywhere there's a y, I put an x. Everywhere there's an x, I put a y. Step 3, now we're going to solve for y, but y is stuck in the exponent. So the rule of thumb is to convert this to logarithmic form. So I will start by writing log. The base is the base, right? The base is 2. That becomes the base of my logarithm. Skip over this part. The logarithm should equal the exponent. The exponent in this case is y plus 9. So by elimination, x is what goes inside the logarithm. Now y is out in the open where I can solve for it. All I have to do to get y by itself is cancel out this plus 9 by subtracting 9 from both sides. And I will end up getting log base 2 of x minus 9. So remember, that minus 9 does not go inside the logarithm. It stays outside of it. You just kind of tack it on to the end of that logarithmic function. Equals y. And then step 4, final step, replace the y with the inverse function notation. So you get f inverse equals log base 2 of x minus 9. And there is the inverse that you should have come up with. All right, so sorry that video also went a little extra long, shorter than 4.1, but a little longer than I would have liked. But that concludes section 4.2. Thank you for watching. If you're one of my students and you have any questions, please make sure to contact me. See you for section 4.3.